So do you have another 2 days? You're not following Piazza?
I was just on there.
Oh, okay.
That was a while ago.
Okay, yeah. So anyway, the homework is due on Thursday instead. If you finish, that's fine. Take a break. Okay, so I thought we could talk a little bit about the homework if anyone has questions. This was a plot, I think maybe Ben made this one. You would expect it to look maybe something like this. This was hand-over-hand locking. I don't know. Just an idea, like what does a decent plot look like? Okay, who's finished the homework? Almost everyone. Okay, half. Okay, right, good. So I guess the hand-over-hand locking was the hard one, probably, or was it harder to parse the text files? No. Hand-over-hand locking was the hard one. Yeah, I mean there's a lot of tools to start typesetting documents if you haven't done it before, and so there's that too. But in any case, for the hand-over-hand locking, did anyone have any questions on that? Yeah.
So it's just more of an implementation question. Like, is it necessary to use to grab the next node of the one that you're trying to delete to lock it? So I was like just thinking about it, just like mentally. It doesn't seem like that you could run into problems, but we did discuss it in class a little bit, and you kind of went back and forth.
Let's see. Is it necessary to hold a lock for the node that you're going to delete?
After the node you're going to delete.
After you're going to delete it? No. The one before, certainly. So it's the ones that you will make changes to, or you want to prevent someone else from making changes to. So the one you're deleting, you want to hold a lock so that no one can insert a node, like changing the next pointer to insert. And the one before, you want to hold that so that no one can change the pointer of the previous node on you. Okay, so I actually started experimenting with the next homework and ran into some interesting details there related to what we were talking about last time. We were talking about, let's see, let me find the notes, yeah. This one, a lock-free list. So this is pretty good. Let's see. The lock-free list, point being, we can, even the writers don't need to hold a lock on the nodes, on any nodes, not even the ones they want to modify. So how do we do that? Well, we use this atomic operation, the compare and swap. I think this one is supposed to look like a delete. And so the delete, actually, that's where I ran into trouble. Delete is a lot more complicated than you'd think. So let's call this an insert instead. Old, previous, next. Okay, new node. Okay, so this is a insert operation. And that's all fine. So basically, if it turns out, let's see, right. So if it turns out that someone else went and changed this next pointer before you got to it, then this compare and swap will fail. And what do we do in that case? We don't have much choice in a lock-free list. We basically have to start from the beginning again. We don't really know which the previous node is anymore. There could have been a lot of insertions in between. We don't really know where we should be adding our node. So we start from the top, run down, and try to add the element again. I think there was a good question from someone in class. Is there any guarantee that this will actually finish? Like, could we end up in a case where we're always just failing over and over again? And I think that there's no guarantee for a single thread, because clearly you could get really unlucky. But there is a guarantee for the program as a whole that it always makes progress. And that's what makes a lock-free list really nice. There can't be any deadlock. In this case, the argument goes, if this cast fails, that's because the previous next pointer had changed. that means that someone else made progress. So as a whole, the whole program is always making progress. If it hasn't changed, well then we will change it, so now we're making progress. So then if it's sort of a limited duration program where all the threads need to finish some job, well then we're guaranteed that this thread will also finish its job because someone else will finish first. But if they run forever, then I guess in a very unlikely scenario, you could end up with this thread actually never making any progress due to some sort of unfairness situation. I haven't really looked into that. Okay, so that's insert. Not a whole lot can happen. But there's a really interesting situation for delete. And delete was already interesting, if you remember, for RCU. We had a weird garbage collection or memory management situation. It gets even more interesting for compare and swap of a non-locking list. So let's take this example here. Right, okay, so these are nodes, and we have our next pointers. And point being, now if we want to insert something, just to show you how that works, it works in these exact steps. We allocate a node, then we assign the next pointer from this node to that one. Maybe I should make these all arrows. Where are they? There. Yeah. So far we haven't changed the list, right? We just added this thing, and then we do, suddenly I would do a compare and swap, and we change this pointer to point here instead. Oh. And that's done in one step. So if someone else had made this change, then it fails, and we have to retry. Okay, that's easy. But what about a delete? Really? Didn't want to remember that? Oh, okay. Never mind. No arrows. Maybe. Does that work now? No. Okay. I'll have to figure that out some other time. So, all right, so we want to delete. So what do? Well, we should do an atomic change of this to point there, right? And so now this one is inaccessible. We've removed this. This is inaccessible, and we're good. Except something could have happened in between. Any ideas? So this is an atomic change. No one else is going to change the same next pointer at the same time. That's not an issue. Something with a middle node, yeah.
Someone points someone inserts by pointing the previous next to the now unreached to the node which should not be reachable.
Not the previous next, but if you add something from here, yeah. Right? So we do an insert, like actually let me do them in the right steps, in the right order. So we go like that, and then we've already found this one. In the meantime, this change happened. But now we decide to repoint this pointer to up here. So now this deleting this node ended up actually deleting two nodes. Right? So we lost one node along the way. All right, how do we fix that? I thought this is a really interesting example. So linked lists are super simple, and therefore we can go into great depth on the linked list. If we try to do this on, say, a balanced tree, I think you can forget it. Right? In fact, I don't think I've heard of a lock-free balanced tree. Maybe lock-free non-balanced trees, perhaps. But all right. In fact, this is our next homework. An RCU thing. It's called QBSR. You already get a library that implements QBSR. You just have to kind of use, QSPR. It's quiescent state based reclamation, I think. So you get a little library function, and you get to make your readers use QSBR as opposed to acquiring a lock. Right. Okay. And then the other step is we're doing this completely lock-free list. So, how do we prevent this from happening? We would like to kind of atomically remove it, right? But we can't. We can't kind of remove this thing. Someone else already traversed through here. They already have a pointer to this thing. They want to add it to there. So yeah, I completely forgot about this. So then I wrote my own, just to test out the next homework. I tried this out. I wrote this thing with the normal compare and swap deletes just like that. And I'm losing elements left and right. And then I remembered the situation.
You have to check if there are any nodes getting multiple and then point.
Ooh, fix it after the fact. Well, that's going to be really a rabbit hole to go down, I think. But you could imagine, like, so when we decide to free this one, I suppose, we could see, oh, what's it actually pointing to next? That would be nice, but how do we know that this one isn't deleted? I mean, the definition of deleted is you're not reachable from the front of the list, right? From the head of the list. So we don't know whether we should point that somewhere else. What if we mark the node as deleted? Right? We add some marker so that the node is already deleted, and then, well, in principle, I suppose we could try doing your approach. It's going to be really hard, I think, because then you have all these different nodes trying to fix things at the same time, or different threads fixing. It'd be better if you don't make the mistake in the first place. This was the mistake, right? We added a node to an already deleted element. So if we mark the element, before we delete it, we mark it, saying this is actually not a good node to use. And then when this thread tries to insert another node here, it needs to check whether it's deleted first. Right? What do you think?
What if a node adds a pointer before we put the marker?
Yeah. Now we have a problem with atomicity again, right? How do you get the ordering right there? This actually has to be an atomic. Set it to deleted. So you could acquire a lock on the node and then set it and then release the lock. And if you want to set a next pointer, you have to acquire a lock, right? And set a next pointer. Then we're good. Except we're not supposed to use locks here. So the trick is, what if we change the next pointer instead? So it used to look like this, right? Before we do this last one, it used to look like that. So instead of marking the node sort of in a separate field, what if we change the pointer itself? Because what's really nice about that, if we're able to change this pointer so that it looks deleted, we mark it somehow, then when the next thread tries to add, when we try to add this, we do this insert, right? That's a compare and swap, and we see, oh, I had a pointer to here. Actually, sorry, I had a pointer to here, right? It used to look like that. That's what I'm trying to change. So this is actually the assignment I made here. I already have that value. But now suddenly the previous one points at, well, it looks deleted. So then we can fail and try again. It's similar to how the insert would work, right? A normal insert, if we didn't have any deletion, we were just inserting two nodes at the same time. Someone came in before us, finished the insert, and we see, oh, that wasn't actually my previous node anymore. I have to restart. In this case, we can also find out now that actually this one is no longer our previous node. This one is deleted because this link here looks deleted. Okay, so we need to, how do we do that? So there's what if we just set it to 0? Let's start with that. You would very quickly end up with a seg fault, yeah. So if the first thing we do is, let's see here. Here's the proposal. Delete. Mark current next as. Actually, we'll just call it tag. Tag the current next. So if it's tagged, that means it's due for deletion, at least. So you can't use it anymore. So what is this tag? It's basically like cas the current next. And then some tagged current next, whatever that means. Okay, so far we're saying, oh sorry, so tag it means set it to 0, right? We're about to delete it, so why don't we set this next pointer to 0? Then the problem is, the list looks, for a little while, the list looks like this. And now this next pointer is 0. That's really not good. Yeah, we can't make any progress either. But things are just really bad if you have bad pointers here. No, we have to be able to traverse the list until we're done changing this pointer to here. We should be able to continue along this way. But if we change the pointer, how can we continue? We can't set it to 0. We can't set it to -1 or anything. Just some random value. Then suddenly it's not a part of the list anymore. So now we need to change a pointer and still be able to traverse it.
Pointer doesn't use all 64 bits of the address. Use one of the high-end bits.
Yep. Very good. In fact, there's lots of free bits in a pointer. The 16 top, in a 64-bit machine, the 16 top bits are unused, sort of. They have to have the right, have to be all zeros or all ones, depending on what the 48th bit is. But then also the lower 3 bits for sure are unused. Any pointer is going to be 8-byte aligned, at least for something like this. If you're pointing at individual characters, maybe not. All right. But if you're pointing at structs, those are going to be 8-byte aligned, so the lower 3 are also fine. So anyway, we can play with any one of these 19 bits, set down that one as a, well, flip it, I suppose. Like if it's the lower order ones, they should be all zeros. Let's work with the lower order ones because they're always zeros. It's easier. Okay, so we basically set pointer equals pointer or 1, right? Okay, so you can't actually dereference this directly. Then you're jumping to a node that that's not right. But you can dereference it by first nulling out the lowest order bit and then following the pointer. So it's safe. It's a little slower, but it's safe. Okay, so this here, tag, means we set the lowest order bit to 1. And then, now we've said, okay, this is due for deletion, and now we can actually remove it. Actually, we can, oh. I guess we have to do detag that now, because we've updated it. Right. So we set that one, and now we change this pointer to point over here. So at any time during that sequence, we could, like, if something happened, if we try to insert something before we get to set this, right, before this cast happens, right? We're changing this pointer. Well, in that case, this cast will fail. we won't be able to set it to deleted anymore because this next pointer has changed. So then we have to retry. Okay. And this is atomic, it can't happen halfway, so either we set it or we didn't. So in this case, we failed, we retry. Next case, we were able to set this, to tag this pointer, and then this one comes in and it tries to update it. The insert fails, and that retries. And then finally, maybe we've finished the whole thing, and we've set this one as well. Yeah, so for a while it looked like this, right? But then we finally set the last pointer, and again this one is tagged as deleted now. It's not just due to be deleted, it's still deleted. And so this insert will still fail. So if we restart now, we will get to the right node. Maybe it's this one, maybe it's this one. Right? Depends. Actually, doesn't depend. It's probably this one, always. All right. That leaves us with one problem. Sometimes this will fail. We won't be able to. So when could we, let's see, when might we be unable to do this update? We're deleting this node, right? So we set this pointer to tagged. Oh, it's the wrong pointer now. Right. So what could cause this cast to fail? Yeah, so this insert here, it didn't happen against this node, it happened against that node, right? So this is the same as any other, the same as our old deletion, I suppose. Like if someone changes the previous node, well, then we're host. We can't just go and change it again. We have to restart. So now we ended up in a situation with, let's see. Actually, it would have to be, it would have to look like this then, right? So we tried to delete it, but that didn't work. So now we have a list, and we're restarting. And now suddenly there's a list with a tagged pointer in the middle of it. This one was supposed to be deleted. So basically, we're restarting our deletion. We run down the list, and we find our tag pointer, and we try again to delete it. Right? But everyone else, they have to pay attention and sort of treat this as a deleted object, even though it isn't there, even though it's there. Right? This was marked for deletion. That means you can't use the values in there. You shouldn't be adding anything to this node, and so on. So basically, they have to ignore this node if it's tagged for deletion, and then we come back eventually and get to kill it off proper. So as you can tell, there's a lot going on when you're doing lock-free. It's a lot harder than with a single big fat lock or single-threaded. It's almost the same. Big fat lock and single-threaded is pretty much the same scenario. But there's some nice benefits to it. So let's see. I think I got this working right. So I had the big fat lock. Let's do it like this. Run it with 8 threads, say. Oh. Oh. All right. So there's some 64,000. So it all depends on the size of the list, right? How many operations you get. and the number of nodes. Let's try, so I also did this RCU one. So that's 65,000 operations per second. What was it, QSBR? So that's with, so now we have lock-free readers, but the writers are doing a big fat lock. And then finally with the lock-free, right. So, and this actually, the benefits sort of extend further as you add more nodes, add more threads. So here we're getting 1 million operations per second, right? Let's try that with our big fat lock. 50,000, right? So it's worth the trouble. Unfortunately, it is really complicated to get it right. And so a locked data structure will work on any architecture. As long as you use locks, the operation of the locks is sort of its own module. You don't have to worry about how this lock works on different architectures. When the lock is locked, it's locked. That's it. Right? So it'll be fine, other than performance. But for a lock-free data structure, you really have to worry about memory consistency guarantees. So in this case, we're okay because all atomic operations are guaranteed to be ordered, writes are ordered, and so on, right? But on a slightly different architecture, the thing just wouldn't work. You can't compile this C program to run on an ARM. You have to put in a bunch of memory barriers here and there and that sort of thing. So portability-wise, it's probably a bad idea. Point of the next homework is, I suppose, to get a little feel for the challenges of a lock-free data structure. But it can be worth it. If it's an important data structure, you definitely want to consider it at least. Okay. So I think that brings us to the end of normal synchronization. Actually, maybe I should, no, that's okay. We'll talk about the next homework next time. And sort of QSBR library and those things. Any questions on this whole thing before we continue? All right. Okay, so can we do even better is the question. All right, this data structure traversal takes a long time. That's problematic. The writes are, well, okay, so we can use a better data structure, of course, but for the same data structure, are there other ways that we can try to go even faster potentially? Lock-free data structures tend to be fast, but maybe not the fastest. Depends on the, mostly on memory locality of the data structure. So I thought we'd look at a couple of other options as well. One is called combining. Or actually there's a, yeah, combining is good. So for everything we've done so far in synchronization, it's about coordinating, like, when do I get to do the work, right? Or maybe with the lock-free, it's like, oh, did someone else get there before me? But still, the thread is always doing the modification of the data structure directly. An interesting alternative is to just have one thread do the work. And the benefit of that is that now you have, I'm not sure that this applies really well to a linked list, but the benefit in general of combining is that the data structure itself is always in the cache of one thread. So the general idea is ask another thread to apply changes. Could potentially be more than changes, could potentially be reading as well. Okay, so how do we ask another thread to do the work? Well, in combining, the approach is, I guess we could call, actually we should, one of them is called combining. Change it. Okay. So rather than acquire a lock on the data structure, we somehow say, "Oh, I need this done." So let's take a concrete example. We want to insert something into a list. So we say, for an insert, we say, "Okay, try to acquire lock." Let's see. So I tried to acquire some lock, big fat lock on the data structure this time. But then if the lock acquisition fails, instead of a spin loop, which can be quite expensive, just trying to get the lock, I say I add my work to a to-do list. Okay, else. So now I got the lock. If it worked, then I do my work, then do all the work on the to-do list, and then release the lock. Okay, this is kind of conceptual. But so the general idea is we only try to acquire the lock once, and after that, the lock is not being touched. If someone's already doing work, let's see. Yeah, so I add my work to this list, and then if someone else comes in and tries to acquire the lock, they see, oh, there's other work to be done, and they perform it. So how can we sort of describe representing work to be done? Yeah.
Is to-do list common across the threads?
Yeah.
Basically, you're asking someone else to do it.
Sorry?
Basically, you're asking someone else to do it.
Yeah, exactly. So it's a shared to-do list. We haven't decided on a specific representation of the to-do list, but let's think of it as a linked list. You do a compare and swap insertion for now. Yeah.
You could have data structure or whatever, but you would just have operation to be done, and then what value to do on that operation. Insertion, deletion,
Yeah, for sure. We could have something like this, right? That's one way to do it. But an easier way is to just say a function pointer and arguments. Right. So basically, we have a linked list. Actually, let's keep it even simpler than that. So we have a lock, a BFL linked list, with each node holds a function pointer and some arguments. So that's the work to be done. So if you want to insert something, right, we use the insert function and then some internal insert function, whatever, and then a pointer to the node we want to insert. Say. Okay, so what's nice about this is that every time you want to insert something, you touch the lock once, so it's not a busy lock. Right? If the lock is already in someone else's care, then you add something to your list. In fact, I think we have another lock that we're using here. It's not a busy lock again because we're just adding something and we're waiting for work to be done. So we add our work to the list and then we wait on our own little. So let's put another one here. Return value. So now we wait for the return value to change to become a sort of proper return value, and then we know that the work has been performed for us. Yeah.
So is this for the bitpack lock, or you're just having one lock in the entire data structure?
Right. Yeah. So what's nice about this is all of the work is being done by one thread at a time, and so the list will be local in that thread's cache. Whereas if you're using a normal big fat lock, then so you could imagine this linked list of work to be done becoming quite long. Right? So now that one node that's performing all of the work for it has all of the nodes in its cache, and it can do the work faster.
I have another question.
Yeah.
So why not instead of just changing which thread is doing its work, why not just have one thread that just constantly does all this work, just keeps checking for more work to be done?
Yeah, absolutely. That's yet another design. So this is not called combining. This is just, I guess, we call it just delegation. Let's call it direct delegation. No, dedicated. So, okay, so a cool part of this combining design is that if no one's accessing the data structure, you don't need anyone looking for work to do. Right? All the threads can do useful work, and then if they use a data structure that isn't really heavily in use, then they always get to acquire the lock and always can apply the work themselves, and everything's fine. Now, if it's a contended data structure, then it starts being expensive. Lock acquisition starts being expensive. All of these cache misses, for every changed node, you have to invalidate cache entries and all the other cores and so on. A contended data structure can be a problem, and with combining, you end up sort of gracefully transitioning into this delegation framework where a single node is doing most of the work for a while, and then it's done with a to-do list. It escapes, and someone else gets to do all the work next time. But yeah, it has a problem then that the cache isn't always hot. Because when you're done with the to-do list, then it's going to be someone else's turn, and then they have to sort of warm up their cache. So yet another approach is to use a dedicated server. And this is something we've been doing a lot in my group. Yeah.
In the combined approach, because we have a shared to-do list, which is essentially a queue, wouldn't there be contention for the queue to add jobs with you?
Yeah, so I think the idea is that I think the main idea here is that the critical sections for this are really short. You just add something to the queue. It's just like a O1 operation, whereas doing the work can be quite a bit longer and sort of apply to a lot more memory, more cache lines. So you kind of get the delegation benefit from that. But yeah, there's certainly overhead in working with a to-do list. Okay, so the final design, and that's something that we've been doing a lot in my research group, is this dedicated server delegation. And that's really only relevant if you have a lot of hardware threads. You could imagine if you have a 4-core machine, you don't really want to dedicate one of your cores to just spinning to see if anyone needs work done on this data structure, right? Unless it's a really busy data structure. But when you have hundreds of cores, then it's really not a big deal. Then you can easily spare one core to handle various shared data structures. And so in that case, it's something very similar, but there the idea is we have a static request array. And each element in the array looks like, let's go like this instead. It looks again like a function pointer and some arguments and a ready flag. So in the dedicated server case, there aren't any atomic operations at all. Here instead you have one thread, a server thread, that's looping through this array of potential requests to see if there's any incoming request available. So this is a global, or maybe it's on the heap, this array. But the server, all it's doing is running around this array over and over to see, is there any request that's a new request? If so, call the function pointer with these arguments. And then return the value. There's a response array. Actually, we can just leave it like this. No, I forgot. There's more than that. Struct response. Okay, so you can already imagine sort of what this looks like for all requests. If request is ready, call the function with arguments. Something like that. Right, so now we've dedicated a hardware thread to just doing this work over and over and over. But what's really nice about it is that we don't need any atomic operations to do the work. And so, as we've seen, atomic operations slow everything down. And everything's always local. Because the server is the only one that's operating on the data structure itself, you end up with very good cache locality. Can we think of any drawbacks? Let's see. Benefits. Oh. What might be some drawbacks of this idea? Yeah. Single-threaded, yeah. So why is that a problem?
Might not be able to get as many operations there if you can run them.
Yeah, let's compare it to a big fat lock first. How does it compare to a big fat lock?
The same as big fat lock running on a single thread.
Right. It cannot be worse, probably. Well, maybe. But it's about the same as a big fat lock, because there's only one thread accessing the data structure anyway. So if the data structure is protected by only one lock, you could expect delegation, generally speaking, to do better. But yeah, if in the linked list case, for example, if the critical section is long and you can run it in parallel, if you have multiple threads, then it'd be really hard to beat it with a server, with a single threaded server. So now you have 100 threads all traversing the list in parallel versus a single poor server trying to do it. You can't beat it, right? If it's a short list though, it's less obvious, because now most of the elements are being changed all the time, at least if there's updates. The elements are being changed all the time. Every time you update an element, you invalidate all these entries on all the various threads, so their traversals are really slow, whereas the server's traversal will be fast. There's a trade-off. It's always trade-offs in these designs. Okay, so single-threaded. Versus potentially parallel access. Or lock-free. What about this this thing? You have to write. Yeah, go ahead.
Do we also push the read operations?
You can choose. Right? It's the same as with the big fat lock. It's much safer and much easier if you have the readers use the big fat lock as well. But if you apply an RCU model or something, then the readers could potentially run in parallel and then only apply the actual modifications with the server. And so maybe one potential sort of good compromise in the linked list case would be to have the clients traverse the list, but to have the server do the modifications. So then it becomes sort of like the hand-over-hand locking sort of implementation of the server, except with locks, except with no locks, because the server doesn't need locks. It's single-threaded. So we have a library for this too, and I'm hoping we can do one homework where we experiment a little bit with delegation versus locking in a few different settings to see how that works out. I think we'll have to get back to that in more detail when the time comes. Oh yeah, so what about this whole idea of writing requests? Like, it seems like it's quite a bit of overhead here, right? This client is having to formulate this request, right? And then spin waiting for a response.
What if we have another request and the previous one is not satisfied?
Yeah. So each client, I guess there's many ways you could design it, but at least in this sort of standard design, each client gets to have one outstanding request. It's all synchronous requests. And every client has their own request element in the array, so there's no need for any conflict resolution. There's no synchronization necessary. So we send this message, right, by just writing into memory, and then the server is going to have to read that memory to get the message. So there's clearly some overhead involved in that. But it turns out that compared to acquiring a lock, this is dirt cheap. And I can probably point you at a recorded talk about the delegation in general. But the main benefits that you get is that all threads can write to this request array all in parallel, right? Because it's completely unsynchronized. Whereas if you're trying to acquire a lock, everyone has to wait for everyone else to acquire the lock. And then once it gets to the server can very quickly apply these operations. They're usually quite simple, unless you're traversing a really long linked list, in which case we're not going to perform really well with delegation. So for long critical sections, probably not a good idea. Okay, so those are the sort of the options we have available to us. Lock-free, I mean, with no synchronization, nothing, only if it's read-only. Big fat lock, super simple, but can be problematic, at least if you have a contended data structure, like many threads wanting to access it at the same time, or if you have many threads in general, there's more likely to be contention. You have your reader-writer lock. And if you have many readers, then this is pretty good. There's still contention between writers, but at least the readers can run in parallel. Also really easy to work with. And then it gets a little more complicated with the RCU, read, copy, update, where the readers run lock-free, but the writers have to be extra careful to never present an inconsistent data structure to the readers. And that in particular involves the garbage collection of freed elements. It's the most challenging part of RCU. But there's nice libraries for this now, and we'll look at that next time, the library in detail. And then there's complete lock freeness, best avoided, but can be extremely fast under some circumstances. It's nice when you want to make sure you don't have any blocking. Like if you have a thread that really needs to make progress, it can't be stopped by another thread going to sleep, let's say, holding the lock. And in some cases, performance can be very good with a lock-free, but it's really hard to design a properly consistent lock-free data structure. It's something that you can easily spend weeks or months on for a more complicated data structure. I would hope that for the linked list it's not going to be that bad. There's also a paper I can point you at that describes the one that we talked about. In fact, I'll just suggest this as extra reading. Let's see. Here it is. A pragmatic implementation of non-blocking linked lists. I don't know who among you have read a research paper in the past. Okay, almost everyone. Very good. Now would be a good time to start, if you haven't. So this one actually describes the method that I discussed, but they also have some proofs of why it's actually why it makes progress and why it's consistent. It's not quite the same design as the one I discussed, but it's quite close. In this one, they delete any nodes that are marked for deletion get deleted during the traversal of a list, of the linked list, as opposed to doing it only when you're trying to delete. But other than that, it's the same. Okay, so Tim Harris lock-free list. That's the one. Nice paper. Okay, so let's see. Yeah, that was lock-free, and then finally, the sort of the last ditch effort is delegation in the case of flat combining or combining. Nodes sort of volunteer to become the server for a little while. And in the extreme case of dedicated server delegation, you have a single thread that is in charge of any given data structure, and you have to send a request to the server to modify the data structure, or sometimes even to read the data structure. And there's lots and lots of work on how to make these things fast, but we'll stick with simpler designs for now. Okay, so that's basically it for synchronization, sort of synchronization design. Now I wanted to look at lock design specifically. So we're sort of taking one step down. We were talking about how to design data structures with synchronization. But now, if you want to use locks, and generally speaking, you want to use locks. Like this whole lock-free stuff is really exotic and weird and tends to break. And probably you want your program to be portable, so I would recommend using locks. Now, which lock should you be using? So we talked already about the sort of two standard categories of a spin lock and a weight lock. And this one is kernel gets involved, kernel mediated, read, or actually does a CAS repeatedly. So with a weight lock, you say, oh, the lock isn't available, let's go to sleep. And that's really good if you have more than one thread per hardware thread. If you have many threads, actually, let's call this scheduler mediated. So, but this one there isn't that much to it, the weight lock. And so I think we'll leave that alone. We talked about that in some detail before with this futex system call. That's how you kind of tell at least if you're using the OS scheduler, you tell it that, oh, this thread should go to sleep. If you're using user level threads, as in you started one thread, that you told the OS I want one thread, but then you're implementing your own sort of context switch within the thread, then you would have to have your own scheduler that manages weight locks as well, to basically decide to put this user level thread to sleep until we're ready to wake it up again. But spin locks there's a lot going on in spin locks. So I thought we'd dive into that a little bit. Actually, let's move it down. Okay, so your typical one, right? It goes while not CAS. There's a spin lock, leaving some details out. There are a few problems with this. One is if you have many threads at the same time trying to acquire this lock, most of these CASes will fail. And if we look at what one of those operations actually does, it needs to acquire the cache line of the lock, right? It needs to get it in exclusive mode onto its own into its own L1. And there needs to be some sort of atomic ordering between operations as well, so there's some sort of coordination between the cores to do that. So now finally you get the cache line to your cache, and you see, oh, it's taken, right? So now you have 64 threads. They're all doing this. They're fighting over this cache line, trying to agree who should get it next, right? They get it, and they see, oh, taken, over and over. And then finally, whoever's in the critical section, whoever's holding this lock, they finish the critical section, and now what do they need to do to release the lock? They need to get the cache line, right? So there's 64 threads fighting over this cache line. One of them actually wants to return the lock to make it free. But there's no guarantee that it's going to get the cache line next. There's nothing like that. In fact, if these are atomic operations, there's some ordering involved, but there's no fairness. And so it could take a while before we actually are able to free the lock because everyone's fighting over this lock. Okay, so this is the naive test and set spin lock. Okay, so there's another one, a little better. Test and and set. So it goes like this. All right, so this is an atomic operation. This is just a normal read. So the difference here is that you fail, and now, well, you failed because it was locked. So now you're doing a loop here, just reading this variable. The variable is in your cache. Hopefully, for a while at least, it'll be in your cache. No one's writing to it, right? The only one that will get to write to it, oh, let's see. No, it's not quite that good. All right. It's probably not going to be in your cache, but at least you're sharing it with lots of other threads. So every time you read this, you get a copy of the thread, a copy of the cache line, and everyone else nearby on the same socket or other cores, they get copies of that as well, and they all get to see at the same time. Oh, it's locked. Right. And then comes the thread that wants to free it. It needs to tell everyone that, yeah, actually this is pretty good. So you have all these 63 threads. Let's say it's a 64 thread program. One is holding the lock. All the other ones try to come in. They do one of these compare and swaps, and then they're stuck in here because the lock is still locked. So after they've all kind of piled in, now at least it's quiet. Their cache lines are not being invalidated because it's not changing. Whoever's in the critical section, they haven't updated the lock. We're good. And then we want to free the lock. We want to unlock the lock. Then we need to invalidate the cache line for all the other cores. So that's one broadcast message probably. And then we get it exclusive mode on our node, and we can, or in our L1 cache, and then we can write to it. Okay, so here's lots of contention to the cache line. Continuously. Lots of contention for the cache line. Okay, this one is a little better. Lots of contention initially, but every time the lock is released, I suppose. Or maybe after every time the lock is released. Right, so what happens? One of these threads, the one that's holding the lock, sets it to 0. All of them see, oh, it's not locked, right? They all pile in, try to cache it. One of them is going to succeed. So you have another 64 of these kind of piling in, fighting over it, and the first one got it. Other than performance, you see any problems with this design? They both have the same problem.
The cores in the same socket are going to get the signal first on whether the lock has been cleared.
That seems likely, yeah. And that would, why is that a problem?
They may just always beat something on a remote socket. So the remote sockets are going to wait a long time.
Yeah, that's right. You could end up with a really poor fairness situation where, in fact, I've seen it even worse than that, where the core that held the lock wants to grab the lock again quickly. It knows before anyone else that this lock was freed, So you can go back in and take it again. So you get these back-to-back acquisitions 1,000 times back-to-back if you're doing very short time between critical sections. But more generally speaking, you are likely to encounter unfairness that, oh, maybe I got in second, like someone held the lock, and then I got in next after them. I want the lock, but then there's a whole slew of other cores lining up, and eventually it's just a kind of a mob trying to get the core. You gotta get the lock. There's no ordering. There's no fairness in that lock. So we could do a little better than that in terms of fairness. And the solution is called a ticket lock. So this works like at a deli counter or something, where you take one of those little paper slips with a number on it, and then on the wall there's another number that says whose turn is it. So we have the ticket counter and we have the wall counter, and to acquire a lock it goes atomic ink ticket counter. Oh. And then right, and then to release it, it's just a wall counter plus. So what's really nice about this is if you got in second, you're gonna get the lock after. Some problems with it though. So this is not an atomic increment, by the way. Any idea why?
Because you're releasing thread, you already in the thread which has a lock and increment the wall counter.
Yeah, there's only one thread that ever increments this wall counter. It's the thread that's holding the lock. So you don't need an atomic increment for that. Right, okay, so it's fast. Atomic increment is always successful, which is nice. And then we're just doing normal reads. There's not a whole lot of fighting over anything. And then the release is pretty simple. Any thoughts what could be problematic?
If there are a lot of threads making requests, then the ticket counter will just increase, and you have a lot of threads. Like the last thread which comes in has to wait a long time before it can execute.
Oh, okay, yeah. If you end up with a long queue, then it sucks to be at the end of the queue. Queues are like that. But there's no other choice, really. I mean, unless you want to cut in the queue, but then someone else suffers. So there's something else.
You cannot get your lock until the thread before you got it, even if it doesn't need it yet. So if you're waiting the thread before you to grab the lock, but it doesn't need it yet, and
if a thread doesn't need the lock, well, so I guess okay, so in the grocery store scenario, I get you. Like you take a ticket and then you go somewhere else, right? Get some milk or whatever. And the number goes up and the guy starts calling, nothing happens. And eventually maybe you lose your ticket, but
in this case,
people are annoyed.
Yeah.
But so there is something like that going on here too. And it's almost the opposite of the test and set lock, the TTAS. So there's a really nice performance benefit to having the thread that sees the lock being free first, just doing it, right? So if you're standing there at the butcher's, you're the only guy there, right? Everyone else has a ticket with a lower number than you, but they're off in the cereal aisle, right? It's time. You should go ahead, right? So there's definitely a performance drawback to having this fairness, right? There's some balance there that you need to get. There's a variation on this called hierarchical ticket lock. I think there's a small, let's see. So it has something to do with a delay. Wait to get a ticket if you are far from the lock. Something like that. So I'm not familiar with the details, but basically you could imagine that you see who's holding the lock at the moment, and now you know that that's a core that's far away. So you wait a little bit long, like you wait for a moment before you increment that ticket counter. It's almost like looking around in you're at the butcher's, right, and you see that there's someone with a toddler, right, that is about to have a meltdown, so you let them take the ticket first. Right? So here we see that, okay, I'm kind of far away, the lock's way over there at the moment. Let's see if anyone else wants to grab a ticket right now. So you just give a little bit of a delay in between. I believe that's the hierarchical ticket lock. Okay, there's another problem though. We're all doing a lot of spinning over here. So anytime the ticket counter or the wall counter change, and they could be on the same cache line or on different cache lines. There are different benefits to that. It would be interesting to experiment with at some point. But anytime they change, all of these threads will incur a cache miss. That's okay, they have nothing better to do. But at the same time, I'm not allowed to do an increment until all of those threads have invalidated their cache lines. So every atomic increment will go slower because the cache line is spread all over the place in the system. Same thing for the release. Also goes slow. So it'd be better if we weren't all spinning on this really busy, like when you take a ticket, let's see. No, okay. I need to improve this a little bit here. It should say my ticket. Yeah, that's better. Okay, so of course, you have to wait until your ticket number shows up on the wall. Oh, we're out of time. So next time we'll talk about another design that's called a queue-based lock, where everyone spins on a different variable, which can be a lot more stable when you have lots of concurrency. All right, thank you. I'll see you Thursday.